Well, good morning, everyone. I'm Keithan. This is Miguel. That's Emerson, and that's Nick. And we're Mad Tech. And today we're going to be demonstrating our project, which is a small-scale helical wind turbine. Basically, this is a smaller version of a helical wind turbine that's placed under train tracks. And we're going to use this to capture wind energy and supply it to our generator, which can be used later. We came up with this idea because the world that we live in currently is facing a lot of climate change issues. Most of our energy comes from fossil fuels. And so we came up with this idea to make a renewable source of energy. Yep.
All right, so when we were designing this project, there were a couple risks we had to take into account. So the first one and the biggest one that we wanted to address was how we're going to charge our supercapacitor. So to ideally charge a supercapacitor, you want a constant voltage level. So to do that from our generator, we wanted to get a constant current. So we designed a buck boost generator, or a buck boost converter, to keep that level constant. And also a protection system that will switch the load to a dummy load if the capacitor gets too charged, just to protect it from overcharging. So in the real world, where this would be applied under train tracks, obviously it's in the real world. There's going to be rain and snow and rocks and things underneath the train. So in the design, there's drainage holes in the bottom, and we've also designed it with safety of maintenance in mind, because as there are rocks that will be flying at high speeds, it could easily break. So the design is easy to take off of the train tracks, easy to take apart, and parts are easily interchangeable, and they just have to be reprinted, which isn't very difficult.
Cool. So next we have our key components and key technology. So first we have our helical wind turbine, and basically that plays a big part on the conversion between electrical energy to mechanical energy, which is something we were focusing on for our project. When it came for our wind turbine, we were trying to decide which one to use, and we decided on a Savoni's turbine because of its application in these urban environments, since we're going to be placing these under a train, and it will be able to capture the wind flow from underneath a train when it's moving by. Next we have our DC power generator, and that basically is determined by its size based on the torque of the generator. And basically we want our power constant throughout, so when we have a larger torque, we have a lower RPM, and that's something we had to keep in mind as we were designing our generator. And lastly, we have our buck boost converter, and our buck boost converter steps up and steps down the voltage, and that's, as Emerson mentioned, our regulator in our project. So if we have a higher voltage and we need to, our buck boost converter can step it down with our buck, and if we need to boost it up, our boost circuit is able to boost it up to our desired set point. And as I mentioned before, our DC generator is attached to our wind turbine, and that has to keep up constant power, and it's something that we kept in mind through our project.
All right, so I'm going to be talking about the design. We basically have this system right here. This is our housing unit for the turbine. If you can look right here, you can see the turbine in there. You can see it as I spin this drive shaft. So the turbine only takes up this percentage of the housing unit. The rest in here is our generator and our buck boost converter. I'll open it up after the demo, but basically the generator in here is coupled with a flexible coupling to the drive shaft, and that allows, even if the generator is slightly not aligned, it still allows it to be turned pretty efficiently. And then from the generator you get to the buck boost converter. That's just a little PCB that we have in there, and then it connects to our supercapacitor unit. This is going to be acting as our battery storage, and it's basically outside of the unit because that would allow for easier removal and replacement once it does get full. And that's basically our entire design. We have ball bearings on the edge of the housing unit to ensure that the drive shaft spins while the housing unit stays in place. And we also have a removable cap on this side that's going to allow for easy maintenance without having to take the whole system apart.
All right, so now for the demo part, I'm going to describe it now because when we turn on the fan, you're not going to hear anything. So the fan will supply a wind speed of about 25 miles an hour, which is roughly what a passing train would do at full speed. So the wind from the fan will spin the turbine blade. You'll see it. There's a little flag on the drive shaft, so you'll see that rotating. And I'm going to pull up waveforms, which will be showing the charge level on the capacitor, and it will you'll see it rising as we go. So originally we had intended to use like a small like microgrid to show that we could supply the load. However, it ended up being too small of a power to actually show that happening. So we're just going to show it charging up, and yeah, you'll see it.
And just a note ahead, this fan is going to blow at 20 miles an hour. That's the proper wind speed we determined that would be underneath a train at the specific height that we've set through this unit, and we've determined that through scientific studies done on airflow of trains. So I'll just start this up.
So ideally, obviously, we'd have a lot more voltage and it would charge a lot faster, but just with the power level we have, it's really slow. We would have liked to show the protection system that would switch to a dummy load when it got to that level. We've demoed that before, but yeah, we weren't able to get to that level today, but it does charge, so we did achieve that goal.
Yep, and what you were able to see is basically as the turbine was charging, or as the generator was spinning, the voltage generated by the generator went through the buck boost converter, and we have a code running on Arduino, and that's basically on the teensy that we have in here, and if the voltage that we were charging was lower than what we wanted, lower than our set point, we would have the boost converter operate, and that boost converter is going to apply a duty cycled PWM, right? And it's going to increase the voltage to where we want it. So our set point was about 4.4 to 4.5 volts. And so in here you can see there's the cap right there, easily removable. And then you can take all the circuitry out. Excuse the messy wiring job. And here is our circuit right here on the PCB. It's just a simple microcontrolled PW or buck boost converter, and then in here you have the generator. You can see we made a little structure for it so it stays as in place as possible, because we noticed that if it doesn't stay in place, there's going to be a lot of losses through the wobbling of the generator. And then what we learned, first what we learned is, like I just said, if you don't hold the generator completely still, there's a lot of losses with that system, so that's something we wanted to focus on, was making sure that's held as still as possible, and that's also why we have the adjustable coupling for the drive shaft. And we also learned that we were ultimately able to achieve our goal. We set out with a goal to build a train-driven wind turbine, which is going to be able to capture energy and store it in a battery unit. So that's what we were able to do overall as a project. And lastly, we learned that we were able to construct software that's going to properly set the duty cycle to what it needs to be in order to boost the voltage to a set point. This was done using the duty cycle equations for a buck boost converter. I know if you guys have taken power electronics, you would know those. And that's basically just the learning that was applied to this system in order to make it functional. Does anybody have any questions? That's all we have for today. Yes?
Do you guys think that you could see an application in the future where you put multiple of these together on a train?
Yeah.
That's like there's existing ones on highways underneath overpasses for like passing semi trucks, and yeah, there's like 4 or 5 of them right in a row. So ideally we'd have, as many of these as we could get. Obviously you'd have to work out like wind spacing and what's gonna add too much and not get to the next one. But yeah, we'd ideally want to have like a couple of these to make enough power to supply any sort of real load.
Yeah. And also, if you put a bunch of these in a row, you could definitely charge up one big battery unit with that. Yes.
So since the energy has to come from the train, does that increase the power consumption of the train?
Yes, through the research we've done, it barely, like, negligibly increases the power consumption of the train.
How does
Like,
that compare to the power you generate?
it's to the point where the power where we generate is more. Because since this is such a small unit, it's not like it's creating sufficient drag on the train itself. And besides, the area that we're placing this in is gonna be right in front of a rail tie. So the rail tie is the wooden beam that runs parallel to the metal tracks. And that area is basically where a lot of wind converges, like it hits the rail tie and then there's a lot of pressure there. So putting this in front wouldn't really obstruct the wind flow because it's just hitting this unit like it would hit the rail tie. So it's not bouncing it back up towards the train and creating more drag or anything like that, is what I'm trying to say.
Thank you.
Good question. Any others? Okay.
Thank
Thank
you.
you.
Thank you.